Last week, the Event Horizon Telescope project released the first ever image of a black hole. You might have heard about it. And I might have gotten a few hundred requests for a video. And honestly, I wasn't planning on covering it because, well, for one thing, I was out of town when it happened, and for another thing is so many other people have already done such a fantastic job of covering it, like Derek from Veritasium. If you haven't seen his video, you I'll put it, just go look at it. It's amazing. He does such a fantastic, dude makes me look like a chump. A damn chump. One thing I can talk about, and something that I thought was kind of interesting, was to look back at the way we visualize black holes over the years and kind of compare this actual first image of a black hole to the way we've always represented it visually. Because along with everything else, this image is kind of the end result of over a century of speculation on what a black hole might actually look like. Ever since Einstein proposed a black hole, we've been trying to imagine what it looks like where physics as we know it breaks down. Visualizing a black hole has always been a unique challenge for a lot of reasons. For one thing, it's actually really small in the cosmic sense. When gravity pushes things down to an infinite singularity, that tends to, compress things a bit. And the second reason is because they're usually surrounded by gigantic clouds of superheated dust and gas, especially the black holes at the center of galaxies. And the third and most obvious is they emit no light. It's kind of their defining quality. And it's kind of hard to visualize something if it makes no light. So what you basically have is a tiny, invisible object surrounded by very brightly glowing clouds over millions of light years away. Seriously, anybody who says that this image is too fuzzy, it's okay to punch them. I'm not advocating violence, but it is okay to punch them. In fact, they're so hard to capture. Up until now, the only proof we've had was indirect observation. We saw stars at the center of the Milky Way and in other galaxies whipping around invisible objects whose masses would have had to be so large that the only explanation is a black hole. And we heard black hole collisions through the LIGO gravitational wave experiment. But yeah, until we got this image, we couldn't be completely sure that they really existed. Picture it didn't happen, right? So in the old days, they didn't even really try to image the black hole. They just wanted to show how an infinite singularity of gravity would look like, and they did that with wireframes. Einstein's relativity suggests that gravity curves space-time itself, and one of the best ways to do that is the whole, bowling ball in a bedsheet thing. While it does do a good job of getting the idea across, it's still not a visual representation of a black hole. It's really more like a graph of a black hole. Now, unfortunately for a lot of people, this kind of solidified this idea in their head that a black hole is an actual hole that you could fall into. The ultimate representation of this might have come in the opening credits to Disney's The Black Hole in 1979, which at the time was the longest computer graphic in movie history. So this wireframe representation of the strength of gravity, whether it's from a star or from a black hole, it gets the idea across. But it's always bothered me because space itself is not 2D, it's 3D. And if you were to show an actual 3D wireframe of the universe, it would paint a much more shocking picture. We think of space as like the big, flat, empty spaces, but space-time itself is actually a very lumpy, bubbly, doughy mess. Now, science communicators and artists obviously knew that the whole wireframe thing was just a representation of the gravity of a black hole, but they still kind of had that locked into people's minds, so they used it to create more of a vortex image. Going back to that black hole movie, the way they actually depicted the black hole in the movie was more of like a swirling vortex of gas and dust just funneling matter down like water going down a sink drain. Of course, they also depicted this as what would happen if you went through a black hole, when in fact you would actually be spaghettified into a single line of atoms. It would not be very pretty. They took some liberties. But this vortex imagery was something that was already solidified in the public mind anyway. They just kind of used it for this movie. Gravity bends light, which is something we've known for quite some time. It was proven by Sir Arthur Eddington in 1919 when he photographed a solar eclipse and saw the light from a star behind the sun refracted around the sun, which actually proved Einstein's relativity theory. So another popular visualization of a black hole tries to take that into account by showing how the stars and galaxies and stuff behind the black hole would be refracted around it. This is actually a technique in astronomy known as gravitational lensing, where they take the gravity produced by galaxy clusters and use that to bend the light so that you can see much further behind it. But this visualization gets a little bit closer to reality because instead of trying to show gravity as a series of grid lines, it actually shows how it would affect the light itself. Obviously with the black shadow of the event horizon in the center. And this might actually be an accurate representation of a rogue black hole, one that's just out there not around anything else, because all that you would be able to see is the way the stars behind it get refracted. It's really another example of that indirect observation. And rogue black holes are thought to exist, but they are rare. I mean, black holes get formed from gigantic stars that collapse down on themselves, and the reason those stars get so big is because they are born in places that are full of gas and full of dust, and it accumulates from that. So it's most likely if a black hole forms, it's going to be surrounded by gas and dust. Especially the supermassive ones at the center of galaxies. It's just surrounded by matter that just gets beat the hell up. With that in mind, you might be familiar with this image of a black hole surrounded by a disk of superheated gas and dust shooting out jets of plasma. And if you're anything like me, you've always wondered why exactly those jets get fired away the way they do. And if you're anything like me, you run a YouTube channel and you have to look up this kind of stuff. So I did. Turns out, according to a study last December in the journal Physical Review Letters, black holes, when they spin, create gravitational fields. These magnetic fields get twisted and bent all up, which forms electric fields inside of them, which basically work as particle accelerators, firing protons out at a fraction of the speed of light. And this is thought to be one of the places where cosmic rays come from, high-energy cosmic rays. I actually covered that in a previous video. This is one of the things that they think causes them. And of course you can't talk about black hole imagery without talking about the movie Interstellar. That's because it not only featured one of the most accurate representations of a black hole in movie history, it actually broke new ground in science. The visual effects team worked closely with astrophysicist Kip Thorne, who worked out the equations that the visual effects team then took and used to create Gargantua, the black hole that serves as the central plot point in the movie. This was not just a really cool image, it literally broke new ground as multiple scientific papers were written around the processes they created to make this simulation. And the basic gist here, which you should already understand because you should have already watched Derek's video over at Veritasium, is that just like the planets in our solar system formed in a disk around the sun from an accretion disk, the black holes have an accretion disks of their own. Think of Saturn as a black hole and you're getting there. Except there's that whole relativity thing. Since the massive gravity of a black hole bends light, what you actually see is on the other side of that black hole, that part of the accretion disk gets refracted up over it, so that you actually see a double accretion disk phenomena. By the way, if you've ever wondered what a black hole would look like from different angles, there's this animation that shows you, and it's trippy as shit, dude. This is, of course, an amazing visual effect. But they're not the first people to visualize a black hole this way. In fact, back in 1979, just a year after Disney's Black Hole movie came out, French physicist and artist Jean-Pierre Luminet created this. Only he didn't have modern computer graphics, he did this with an IBM 7040 mainframe that calculated the flow of light, and then literally drew it with a felt tip pen on white background, then processed a negative of the image. And there's actually a couple of things that Luminet got right that the black hole in Interstellar got wrong. One thing is that the further it go out from the black hole, the less bright it would be because there's less energy involved there. And the other is that asymmetry that you see there. And the reason for this is basically the Doppler effect. Light that's traveling toward us is going to appear brighter than light that's traveling away from us. And if this accretion disk is spinning around, in this case it's spinning in a counterclockwise direction, then the light on one side would appear brighter than the light on the other side. It should be noted that the Interstellar team was well aware of this, but they chose their version of it for simplicity's sake. And finally, we get to last week's image. This image took over 200 scientists working at nearly a dozen telescopes all around the world, essentially creating a telescope the size of planet Earth to create this, the first ever actual image of a black hole. For 100 years, we've been speculating and interpreting the idea of a black hole in various different ways, but this is the real deal, and it's a big deal. Except, at the risk of nitpicking, this is still sort of a representation because those telescopes all around the world were radio telescopes. What you're seeing here is actually radio waves, which we can't see with our little squishy light collectors. And the reason why they went with radio is because the two black holes that they imaged, which was Sagittarius A, which is actually at the center of our Milky Way galaxy, and the supermassive black hole at the center of galaxy M87, the reason why they did radio with those is because they're surrounded by that super hot dust and gas, and visually we wouldn't be able to actually see any of the light coming off of it. And frankly, a lot of space imagery is done this way. Some of your favorite space images are probably not really visual representations of that. It's not something you would actually see because they're false color images of other parts of the electromagnetic spectrum. It's not our fault the visual part of the spectrum is so tiny. But perhaps the biggest part of all this is it's just another piece of the puzzle, another proof of Einstein's theory of relativity. When black holes were first proposed, most people thought the whole idea was just crazy. And over time we've seen little bits and pieces and been able to show indirectly that they're there, but here we finally have the ultimate proof. All right, I hope you enjoyed watching that. If you did, please do check out maybe this video. Google thinks you'll like that one. And if you like that, maybe check out some of the others, and you might want to just subscribe, because I come back with videos every Monday and Thursday on topics just like this. T-shirts are available at the store at answerswithjoe.com/shirts. They are a lot of fun. They support me. They support a guy over in Prague who designed them and does a fantastic job with them. So you might want to get them. They look good. answerswithjoe.com/shirts. With that, I'll let you go. You guys go out now. Have an eye-opening rest of the week, and I'll see you on Monday. Love you guys. Take care.